Hello everyone. So today we are going to discuss this question. The question simply says that A and B are two square matrices of order 3. We have to find out the value of the trace of AB minus BA the whole cube divided by determinant of AB minus BA. So first of all we should understand how we can find out the trace of any such matrix. So let's understand how we can do it. So we have this to find out. So what I'm assuming for that, let's we are assuming that a matrix M which is AB minus BA. Now you notice if I have to find the matrix M trace in the trace of the matrix M, it's not so difficult. How do we find it? Trace of M is nothing but a trace of AB minus BA, which we can write trace of AB minus trace of BA. But also notice one thing, if we have to find the trace of the AB matrix or the trace of BA matrix, that will result in the same value. It means the trace of AB and the trace of BA I can assume same, and so this is going to be 0. It means what we found as the trace of matrix M is 0. Now since the A and B are the 3 by 3 order matrix, the composition what we found, the matrix M AB minus BA, is also of the same order. It means if I want to write the characteristic equation of the matrix M, it should be a cubic equation. So we know that. Let's assume that the matrix M, suppose I have any matrix by resulting AB minus BA, it can be of any order of, any elements of order 3. Let's say I have this AB minus ABC, then DEF and GHI. I don't care what is the resultant of AB minus BA. But it is sure that if I have to find the determinant of M, let's say that number is some number, determinant of M, let's say some number K or anything like that, but suppose this is M. But suppose I have to find the trace of M, we can also find by just adding AEI. It's not required actually, but I mean to say that it's a 3 by 3 order matrix. We can write the characteristic equation of the 3 by 3 order matrix in this way. Let's say it's a lambda cube minus, here it will be trace of A, so trace of M lambda squared plus, or let me write in a different way. Suppose you want to say this, the constant S1. Let's say S1 lambda squared plus S2 lambda plus determinant of M times I is equal to 0. What are S1 and S2? S1 is the trace of M and S2 is the sum of minors of diagonal elements. And of course, if I have to tell that is S3, then I can write the determinant of M. So this is crucial. The S2 means the sum of minors of the diagonal elements. It means suppose you have diagonal elements A, B, and I here. If I want to show that, suppose I have these 3 elements A, E, and I, diagonal elements. I have to find out the minor of A and the minor of E and the minor of I, and if you add them up algebraically, that will result to the S2. Now this is a characteristic equation we have, and by using this thing, we can find out the trace of this matrix M. How we can find it? The trace of M cube, by the way, and divide by determinant of AB minus BA. So how we do that? Let's do it. Suppose, so what we have is this one. So since we have M is a trace of AB minus BA, and we have the characteristic equation, I can write M cube minus S1M plus S2, sorry, this is M square, S2M plus determinant of M into Y. Now notice one thing, from the previous slide, what we can observe that the trace of M is already 0. Even the trace of M, that is already 0, so I can substitute it there. This is going to be M cube minus the S1 is already 0, so that will be 0 times M square, and S2M, I don't know about that, and the determinant of M into Y. Now this will result into M cube minus, rather plus S2M and plus determinant of M into Y. Now I'm imposing the trace throughout this equation. If I impose, by the way, this is minus sign here, we can see there, that should be minus, rather. That will be minus here, and so here also is a minus sign, and here also I have minus sign, and so on here. Okay, so now I'm imposing the trace over that. So what do you get here? The trace of M cube plus S2 is a constant value, so we can take it out, and I can write trace of M. Because suppose you have a matrix and you're multiplying a constant to it, it will multiply each entry of the matrix. So if you're finding the trace, even if you multiply first to each entry and find the trace, it's the same as if you find the trace first and then multiply with this constant. And here also we can observe the determinant of M is a constant value, so we can take it out, and this is nothing but the trace of I. Now this trace of M we have already evaluated, that is going to be 0. So we have to, what we get it here is trace of M cubed is equal to determinant of M times trace of I. And I is the identity matrix, so trace of I is always 3 because we are adding the diagonal entries. So what we got it is trace of M cubed by determinant of M is equal to trace of I. And you notice this is the thing we have to find out originally, the trace of M cubed by determinant of M. And trace of I is nothing but 3, so our answer should be 3. In this way, if you have any matrix, AB minus BA structure, and this question was framed like that, we can do it. We can do also some depth calculation if we understand the characteristic equation and how the trace is actually related to the characteristic equation. Like, suppose I have a question in this. Suppose I have a question, like suppose I'm taking the equation, let's say 3a square plus 5a minus 26i is equal to 0. After getting this, suppose someone asked that what is the value of trace of a? So trace of a square or trace of a cube. Notice that here the matrix is not given at all. Only the equation the matrix satisfies is given to us. Means the characteristic equation at the place of lambda we substituted A, and it is from the Cayley-Hamilton theorem that the equation is satisfied by the matrix itself. So here already we have this equation. Then by using this equation, how we can trace the value of trace A square? So for that, what we can do, you notice here, if I have no matrix given, I have to anyhow find out the A square in terms of something. So what are you going to do? Let's multiply A inverse in the entire equation. In this way, what we have is the first term will become A square. And everything I can send to the right hand side. And this will give you 3A plus 5I and minus 26A inverse. Now suppose you want to find the trace of A square. I will impose trace to entire equation, both hand sides. So what I'm getting here is 3 times trace of A plus 5 times the trace of I minus 26 times trace of A inverse. Now, the trace of A, of course, in the question they will give you that what matrix is satisfying this thing. Even if the trace of A is not given, we can find it out because you know this is the characteristic equation. This 3 is sitting at the place of sum of the diagonal elements, and so the 3 is the trace. So here, you notice the trace of A is already is given the value 3. So this I can write 3 into 3 plus 5 into trace of I. So 5 into I is actually 3 and 26 into A inverse, the trace of A inverse. Now the question is, how do we find the trace of any inverse matrix? So here there is one important note we can take care of. The note is this: the trace of A inverse. How do we find it? So the idea is that if lambda 1, lambda 2, lambda 3 are characteristic roots here of any matrix equation or eigenvalue, any characteristic equation, then characteristic equation satisfied by A, that is satisfied by the matrix A, or I can directly say that is the characteristic eigenvalues of the matrix A, delta lambda 1, lambda 2, lambda 3, 1 by lambda 1, 1 by lambda 2, and 1 by lambda 3 are the characteristic roots of this A inverse, means the 1 by lambda 1, 1 by lambda 2, and so on. So how we can use it? You know that the trace of A inverse we have to find out, and suppose this is our equation actually. From there we can of course form the characteristic equation. How do we form it? This implies the lambda cube minus 3 lambda square plus 5 lambda minus 26 I, not I, sorry, 26 is equal to 0. Now this is our characteristic equation. We know that the sum of roots we can find from here. So don't we find lambda 1 plus lambda 2 plus lambda 3? We can find it out. That is going to be 3. We can also find the summation delta 1 delta 2. Means lambda 1 plus lambda 2, lambda 1 lambda 2 plus lambda 2 lambda 3, lambda 3 lambda 1. This product we can find from here is a minus 5. And the product lambda 1 lambda 2 lambda 3 is going to be minus 26. Sorry, this is going to be plus 5 rather, and that is minus plus minus. Here no sign change, and here 26. So after getting these things, suppose I have to find the trace of A inverse. The trace of A inverse is the sum of these values. So here I'm finding it in the corner. So I have 1 by lambda 1 plus 1 by lambda 2 plus 1 by lambda 3. This is nothing but in the numerator what I got is summation of lambda 1 lambda 2 and divided by the product of lambda 1 lambda 2 lambda 3. You know that this value is going to be 5 and this value is 26. We can substitute it there, and from there, if I have not done any mistake in any calculation, our answer should be rather this one. Okay, so 3 into 3 is 9. So that is going to be 9 plus 15 and minus 26, 5. So I think the trace of a square I am getting is how much? 25 minus 4, 19. If I have not done any such mistakes. So this is a way we can find it out, these kind of questions. So I know that this characteristic equation and the eigenvalues are not in the syllabus of the JEE Main or the Advanced, but it's worth understanding. And if you do that, of course, some questions we can do it very easily. Even if the matrix is given, we don't have to multiply 2 times and find a place. Or maybe the suppose if the matrix is given of the order 3 by 3, again we don't have to multiply the matrix 3 times to find out the trace. We can do it in this way and we can find it. So thanks for watching. See you in the next video with some other questions and some other concepts. Stay math active.